Hi, so this is my HPLC model. Quick little overview. We got a sun for the injector, stripes on the MS, and scary looking solvent. I know. I just thought it looked cool. Okay, so we'll just get right into it. So we start off with our solvent system. And I know I just drew one, but there's multiple solvents in the solvent system, but they're kind of hard to draw, so let's go along with it. So the HPLC utilizes a multi-solvent system. This allows us to control the amount of compound components that are going through the column at any given time. So we can change the polarity of our mobile phase by changing the ratio of the solvent system, so using more of one solvent than the other. And an example of this is if we have a nonpolar compound that is stuck in the column, we can change the polarity of our solvent system to be more nonpolar so that the compound will elute quicker off of the column. One thing that we must make sure of is that the solvents that we are using in our multi-solvent system are miscible with one another. Miscible means that they will mix together and form a homogeneous solution, because if the solvents are not miscible with one another in the system, they can form globules in the column, which clogs up our column. So from our solvent system, we go to the pump. So at the pump, we deal with the dense stationary phase in the column, so that we need pressure to push the solvent and our sample through the stationary phase quicker. And at most universities and at TU, the amount of pressure that we are using to push our solvent and sample through the stationary phase quicker is a range between 300 to 400 bars. So from our pump, we have our injector site, which has our auto sampler port with a little sampler. I know it's a sun. It was really rainy and I was wishing the sun was out, so I made the injector a sun. And at the injector, we have our auto sampler, similar to one that we have on our GC model, which is right down here. I just made a little arrow. The samples stay in their liquid phase throughout the whole entire system, and this allows us to analyze molecules that are much more complex and larger in size than we would with the GC. And at our injector site, we have vial inserts that we can use on a sample that's on a microliter scale. Oh, okay, done with the tongue twisters. We use the vial inserts so that we don't have to dilute our samples to a larger volume. A difference in this with the GC is that the GC heats our samples into gas phase, and we don't want to do that with these large and complex molecules because of their complexity. They are not stable at higher temps. That's why we leave them in their liquid phase. So from here, we go to our HPLC column, which we have the guard, which is at the beginning with the column. And with the guard and column of our HPLC, the column is anywhere from 5 to 25 centimeters in length, and it is made of a stainless steel. And it's made of stainless steel because this allows it to have protection and to withhold against the high pressures that are coming from our pump, the 300 to 400 bar pressure pushing the sample and solvent through the system. And the guard at the top up here, its job is to protect the HPLC column from contamination. For HPLC, the most common stationary phase used is the packed column. And this has the advantage that when our analyte is traveling through the material, when it's traveling through this material, it promotes interaction with the stationary phase. And so imagine that you're trying to pump your sample through a tube with only a coating on the wall. Interaction between our analyte and the stationary phase would be very minimal and limited, and not homogeneous, which is what we want, which would give us a bad reading and would probably result in band broadening, which we are trying to avoid. And so with a column that is packed with beads that have various compounds attached to them, based on the polarity that we want for our for the analyte that we're using. And so the most common beads that are used in our packed columns are the carbon 18, which are nonpolar, and that's for the stationary phase, which means that the beads have 18 carbon chains attached to them, an 18 carbon chain attached to them. And so if we are wanting to change the polarity of our column because of our analyte, we can use different beads that obtain different compounds attached to them, such as like a completely new substituent, or we can manipulate the length of the carbon chain by shortening it or elongating it. And so from our column, we're going to flow to our tandem mass spectrometers, our MS. They are in a series, that's how they're connected. And the MS is placed after our HPLC because the HPLC is going to separate our components first, and the MS will tell us the molecular weights of our components. And the first MS, this one, it acts as a mass filter to get an initial reading of the components to find a possible parent ion, and the second one analyzes the compounds that fragment from the initial parent ion. And this info about the compound that we receive can help us work backwards to determine the parent ion from the fragmentation patterns. Now, tandem MSs, they break down selected ions into fragments, and the fragments are then reveal the aspects of the chemical structures of our ions. And so once the samples are ionized to generate a mixture of ions, the precursor ions of a specific mass to charge ratio are selected in the first MS and then fragmented in the second MS to generate a product ions for detection. So to get different fragmentation for our mass specs, we use different ionization methods. Usually we use the electrospray ionization, which is a soft ionization method, so that the compounds can be analyzed coming off the HPLC first and not instantaneously fragmented. A less common ionization method used is the electron impact method, which is primarily used in GC because it fragments the parent ions before it gets to the MS, which that's not what we want. We want it not to be fragmented before it gets there. And another one is the APCI, which is the atmospheric pressure chemical ionization. It is less commonly used. Its main use is on polar and less thermally stable compounds that have a molecular weight less than 1,500 daltons. A little quick note about mass specs is that the MS equipment is very expensive and are difficult to maintain. And an example of just how expensive it is that the turbomolecular pumps within it cost $10,000 to maintain. So you can imagine how much expensive a whole thing is when a little pump is just $10,000. And so after the MS tandem, I decided to attach my detector of a UV vis, and the UV vis is an absorption spectrum for the compounds and will absorb the compounds with their molecular weights. The UV vis is a fast and simple and relatively inexpensive method to determine the concentration of an analyte in a solution. It can be used for simple analysis to do a quantitative analysis to determine the concentration of the analytes within a sample. In the UV vis, what happens is a beam with a wavelength that varies, usually between 180 and 1100 nanometers. It passes through your solution that's in the cuvette, and the sample that is within the cuvette will absorb the UV rays, the UV radiation, and the UV vis absorption spectroscopy, excuse me without the tongue tying up, the UV vis spectroscopy is the measurement of the attenuation of a beam of light that passes through or reflects from your sample surface. And so as the molecules go through the UV vis, they are absorbing at different wavelengths in the spectrum. The detector can then analyze the molecules passing through it either non-selectively or selectively. So we could choose a wavelength that we think is pretty relevant for your UV vis detector to emit, and the detector will tell you what compounds pass through it at the light after the compounds have been separated. And one thing that we need to make sure happens is that our analytes and our solvents are absorbing at the same wavelength. An advantage of UV vis is that it can target specific analytes and you can see when they come off. And a disadvantage would be that you need to make sure that both the analyte and the solvent have the same wavelength. If our analyte and solvent don't have the same wavelength, then we could get different peaks that are hidden behind one another, or you may only see the peak of your solvent or the peak of your analyte and not both. So you want to make sure that you have two distinctive peaks at the same wavelength. And as the compounds pass through, we have our waste system for the fractions and just for waste in general coming off your column. And then, so once everything has gone through the whole system, it is then all the information will be at our computer where it will be analyzed and integrated, and you'll be able to read what is going on based upon the peaks. And so yeah, this is it. I'm sorry, I know it's long. This is her. She looks like Oklahoma. I hope you like her. I hope you like the sun and the stripes. Okay, thank you.